Thank you so much for the introduction and for the opportunity to present to you a little bit about our technology that we use in electronic scrap recycling facilities. You've already heard quite a bit about the type of technology that we use as well. I'm going to focus a little bit on the processing of flat panels and also talk a little bit more about the preparation of the material to make the optical sorters work as well as they possibly can. As far as a company and a process that we're trying to do, what are we trying to do? We're trying to go from low-end reuse of the materials to high-end recycling. We're trying to go from manual sort lines to highly automated and fully automated sorting systems. So what I'm going to be talking about a little bit today, quick company overview and history, where are the applications that we currently see in the WE area, material preparation, pre-processing, and then I'm going to show you a list of examples where we've installed equipment with some pictures of before and after sorting. At the end, I'm going to talk a little bit about the advanced controls and statistical information that we can extract from these machines that will help you track and monitor your process and make your process as efficient as possible. MSS is part of a group of companies. It's a family-owned company out of San Diego. There are two divisions in the company. One of them is operations. We operate a few recycling facilities, of which 4 of them are actually electronic recycling plants. And then we have the manufacturing division, which is divided into these 4 companies that you see at the bottom. The CP Group is a turnkey system builder. Kraus specializes in construction and demolition, sorting and processing equipment. MSS, the optical sorters, and Advanced Smurf is the controls group for the complete system integration of these systems. As far as optical sorting applications for we always tell our customers that are interested in our technologies, you have to go where the value is. And so where are those? You see a quick list here on the screen. It's recovering residual metals downstream of conventional magnet and eddy current separation systems. So we want to remove and recover the wires, any stainless steel that might have passed through the upstream metal sorting equipment, and any entrapped metals, for example, screws built into plastic pieces. Then the further separation of the non-ferrous metals, aluminum, copper, brass, etc., to generate higher value commodities. Separation of the circuit boards, and at the end, on the lower end of the value chain, is the separation of different plastic resins. I'm going to talk a little bit about the material preparation because it's just as important almost as the optical sorter itself. And if you imagine, you're probably all familiar with magnets and eddy current separators. For those pieces of equipment, it's just as important to prepare the material so it can work as well as possible. It's the exact same for the optical sorter. If the material is not prepared well, the optical sorter won't be able to work as well as it can. So the first thing in we processing is a liberation of some sort, shredding most of the time, where the material is liberated from each other so that the individual fractions can then be sorted from there. We prefer for some sizing to occur. Sometimes that's a little bit of a limiting factor because the volume might not be there to install a lot of sizing equipment, but at least one of the things that we normally do is remove a fines fraction, and mostly because the fines fraction, while it could possibly be sorted on the downstream equipment, it's not very efficient because the smaller the particle size, the lower your throughput on the same type of equipment will be. Depending on your input material, you might want to do an air classification system of some sort, as you've heard earlier in the session, of light versus heavy materials, especially if you have a lot of really, really light plastics, and you might be able to screen or air classify some of those out to make your optical sorting step more efficient. Removing the ferrous metals prior to the optical sorter always makes sense as well. It's a very easy, fairly low cost type of separation, so we always recommend doing that first. A pre-separation of the non-ferrous metals, if your content of non-ferrous metals such as aluminum is quite high, an eddy current separation step is always recommended to, again, have the optical sorter then work on the subsequent steps downstream. From a mechanical design point, it's very important to spread out the material properly on a vibratory feeder most of the time, so that the material is presented to the optical sorter correctly. And you also want to make sure to deliver the material reasonably even over time, so that you don't have surges coming from an upstream piece of equipment. So just to give you some visuals on what I was talking about earlier, so the sizing and material liberation using some shredding technology, using a vibratory feeder or maybe even a trommel to remove some fines, air classification steps, magnetic separation, either via overband magnet or, excuse me, or via drum magnet, eddy current separation. As far as the optical sorting technology is concerned, I'm going to focus on 3 types that we offer and that we've installed in we applications. Our Elvis unit is our high-resolution camera sorting system for sorting of the material by color and by shape. The Cirrus is our near-infrared technology, so we can sort different types of plastic resins from each other. And the metal sort is our induction-based metal detection technology. Now, some of these technologies can be combined with each other, but you'll see that in some upcoming slides. Just to give you a little bit of a visual of what these machines look like, this is one of our color separators installed in actually an auto shredder facility where we're sorting stainless steel and wires from leftover plastics. There's an installation in Japan where we're sorting out residual contaminants from a grinded or shredded copper stream. There's an installation in the southern part of the United States for more conventional WEE material, sorting circuit boards and wires from plastics. And this is one of our near-infrared units in one of our Atlanta installations, where we sort out circuit boards, different types of plastics, etc. Of this particular machine shown on this picture, I have a little video prepared so you have a little bit of a visual of how these optical sorters work. So if you could please roll the video right now, that would be greatly appreciated. This system is installed on the south side of Chicago in the United States, and it's a batch processing system. And it's there we go. It's a batch processing system downstream of a blue box system. You may have seen the blue box upstairs that treats mostly flat panels. And this is just a quick overview of how we're feeding the material. It's fairly small material, only about 30 millimeters or smaller. So the screw auger works quite well to transport that. You have the vibratory feeder that distributes the material evenly over the width of the conveyor belt. You have the detection happening right here in the highly illuminated area across the width. And then as the material comes off the belt, we have the air ejectors to then separate the targeted materials. You'll see a shot from the side here in just a second as well. Have a little better visual of the different ejection chutes. This particular machine has actually 3 output chutes, number 1, number 2, and number 3. And so in one step, out of 1 input material, 3 output fractions can be generated. So in this particular system, we separate a variety of materials by rerunning the material through the batch process as well. A few examples here. You got the circuit board product. You got the plexiglass product that's a little dark, but hopefully you can see it down there. You got the aluminum product, and you can also extract some of the different types of plastics. On this particular case, just collect all the black plastics together. So hopefully this gives you a little bit of a visual of what we can do there. And if you could go back to the presentation, I would certainly appreciate that. Just to give you a few more pictures of what this process looks like when we process the flat panels. On this particular slide, the first step that we did in this particular sample was separate all the metal containing materials from the plastics. So in this particular mix, you'd have the metals, you got the circuit boards, you got the wires, and for this particular test, we also sorted out the LCD, the liquid crystal material actually. and the other one left would be the mixed plastics. Now when we take the metals that you saw earlier, that mixed metals fraction, and we sort out the copper and the circuit board, oops, excuse me. So this is what it looks like with the copper circuit board fraction here, and still the residual metals, or mixed metals right there. We take that fraction here one more time, and we take out, as I mentioned earlier, the liquid crystal fraction right here. Then we take this one more time, and we get out, we extract the aluminum from that mix as well. On the plastic side, remember at the very beginning we generated a plastic fraction. We can extract some of the valuable materials such as the plexiglass right here. There's still some remaining mixed plastics left. So this just gives you a little bit of an overview of what we can do with materials from liquid crystal, from LCDs or flat panels. A few more examples of what we can do with the optical sorting technology. This particular one uses the high-resolution camera system. You can see a contaminated copper stream here, and once you run it through the system, you get a pure copper stream here, and you get a residual, mostly plastics fraction on that side. More traditional types of weave materials, input material, you extract all the metals, so you see little pieces of wire, you see circuit boards, you have pieces of plastics with screws in them or other metal particles, and you have a pure mixed plastics right here. Another example, again, mixed plastics, and you sort out all the metal containing particles here, whether it's circuit board wires, stainless steel, or plastics with metals, pieces of metals attached to them. One more example, this has actually not gone through more of a traditional shredding process, but more of a granulator. You see the particle size is quite small, it's probably less than 8 millimeters or so. And again, we're just sorting all the metal contaminants, or metal containing particles out of the stream with, you can see here, the pieces of circuit boards, pieces of wire, etc. And this is the last one. This is more from smaller household appliances with more mixed and clean plastics right here, and the wires and the metal fraction right over here. One of the things I wanted to point out as far as the capabilities of these optical sorters, obviously they perform the separation of the different materials as you saw, but one of the things we can do is actually collect all the data and look at different statistics from these processes, whether we have a complete plant where you have portable screens like you see here, or you can use advanced statistics to give you information of how the system is running, whether you look at material, big material surges over time. Obviously, we would like to see a much more even or smooth process of the material through the line, or whether your material on the belt has been delivered by the vibratory feeder correctly. For example, in this picture, if you imagine this being the direction of the conveyor going, that the machine is overloaded on the left side but underloaded on the right side. Obviously, you would like that distribution to be much more even to get the best out of the machine, which is really what we're trying to do here. So the machines have the capabilities to provide you a lot of information as far as composition, as far as how they're running, so you can optimize your process in the machine itself, but also upstream or downstream of the machine. So that concludes my presentations. I'd be happy to answer any questions. Thank you.